I want to do an example utilizing conservation of angular momentum. And this is a favorite one of mine. I ask on test all the time. So I have two objects, and they each have the same mass. They're spinning on the same axle, frictionless, no air resistance, that sort of thing. But they're spinning with different orientations. And so this top mass has a angular velocity of omega naught, and the lower mass has an angular velocity of negative omega naught. So if I say sort of up is a positive orientation, then this would be sort of spinning that way, and the one at the bottom would be spinning with the opposite orientation. Okay, so they can slide along this axle, and so you lower the upper one until it comes into contact with you lower the upper one until it comes in contact with the lower one, and then the resulting frictional forces between the two objects bring them to a common angular velocity. And the answer is, what is it? Well, can we apply conservation of angular momentum to this? And the answer is we can, because there are no net external torques to this system. They exert torques on each other, but there's no net external torque to the system. The axle is frictionless and along the center of mass of both objects. So angular momentum is conserved. You can think of this as the angular momentum analog of the perfectly inelastic collision. We had these two objects with different angular velocities. They come together and then stick together, eventually rotating at a common angular velocity. Okay, so if angular momentum is conserved, then we know that our initial angular momentum is equal to our final angular momentum. I'm just going to deal with their magnitudes at the moment. I take that back. We will have to deal with the vector form, but it's essentially a one-dimensional problem. The angular momentum is either pointing up or down, which we will determine via the minus sign. Okay, and so initially we have so this is, say, the upper one's 1 and this is 2. Our angular momentum is equal to the angular momentum of 1 plus the angular momentum of 2. And in our vector form, we found that the angular momentum of 1 would be the moment of inertia of 1 times omega naught, and then our moment of inertia of 2 times negative omega naught, okay, for the different orientation. All right, and so so what is this? Okay, so the moment of inertia of 1. These are uniform disks of. Oh, I mentioned it. I didn't write it down. If this one has a radius r, then this one has a radius 2r. Okay. So the moment of inertia of disk 1 for a uniform disk is 1/2 mass of the disk times the radius of the disk squared. So the moment of inertia of 2 is 1/2 the mass of the disk times the radius of the disk, which is 2r squared. Okay, so which is equal to, there's 4, then it's 2 mr squared. So our initial moment of inertia, then, the initial angular momentum is equal to 1/2 mr squared omega naught minus 2 mr squared omega naught. So our initial angular momentum then was negative 3/2 r squared omega naught. All right. So what happens then after they come together? Now they're rotating at a common angular velocity. So in the final stage, we have a total angular momentum. Now they're just rotating as one object, so that one object has some moment of inertia times some angular velocity that the entire system, at which the entire system is rotating. Okay, so that moment of inertia is simply the moment of inertia of the two disks, I1 plus I2, times the new angular velocity omega. So that's just 1/2 mr squared plus 2 mr squared times omega, which is equal to 5/2 m r squared omega. So I'm going to just use this space up here. If our initial is equal to our final, then these two have to be equal to each other. Okay. So we have 5/2 mr squared omega is equal to negative 3/2 mr squared omega naught. The mr squareds cancel, the 1/2s cancel, and our final angular velocity is equal to negative 3/5 omega naught. So the magnitude is slower, 60% of omega naught of each of of what each of them was spinning originally, and the result is traveling in the negative omega naught direction. So they're going the orientation that the larger mass was rotating initially. But the procedure is the same as looking at in the previous video. You have no net external torque on the system, and so the initial angular momentum is equal to the final angular momentum, and then it was simply a matter of adding all the angular momentum together. Initially, you had the angular momentum of the two objects spinning separately, and so this is the initial. And then final, you had the angular momentum of the entire object rotating at the same angular velocity. And then equating the two, we were able to establish a relationship of the final angular velocity relative to the initial angular velocity.